So the thing I want to talk about in these last couple of videos for this day of lectures is a technique that we can use to measure the amount of heat transfer. And this is something that we will be doing in lab or may have even already started on in lab. But this is known as calorimetry, which is just simply a technique used to measure the amount of heat transferred. So if we take a hot object and put it in a cold object, we'll be able to measure how much heat is transferred. And from there, we'll be able to calculate a lot of different aspects of that. We can use that equation here, this Q equation, and be able to figure out the specific heat capacity of an object or how much mass was added and so on. This technique uses something called a calorimeter. Now, a rough kind of way to describe a calorimeter is usually water is used, and we have that water set at some temperature. Like, for example, let's say it's at 25 degrees, and we put a hot object in there. So, say a hot piece of metal, and it's at 100 degrees, and we put it in this water. And we mix it up, wait a few minutes, take some temperature readings, and over time, we would expect that the water would increase in temperature and the piece of metal would decrease in temperature. And if we measure all those temperature changes carefully, we'll be able to figure out maybe what the specific heat capacity of that metal is. And that's kind of like a rough diagram of a calorimeter. Let me show you a little bit some more precise ones, because one of the things that's a requirement of calorimetry is that everything must be well insulated so that heat isn't lost to the surroundings. Now, the type of calorimetry we're going to be doing in lab or have done very close to this lecture is known as coffee cup calorimetry because we literally use styrofoam cups. Styrofoam has a very good propensity for insulation, so it minimizes the transfer of heat to the outside surroundings very well. And we basically take a known mass of water and its known temperature, and we put a hot object in there. Or we can do a chemical reaction. I'll talk about this in the next video. We could do a chemical reaction in that water. And we measure the temperature change until both substances are equal in temperature. Now, a little bit more of a kind of more high-tech version of a calorimeter. We use like really heavily insulated metals to accomplish the exact same thing. But again, it all relies on this concept of we put a hot object in a cold object and we measure the temperature until both objects are equal in temperature. Now, the way we do some calculations with this, because in theory, the heat that the object loses. All right, so notice I'm using a negative sign for Q because it's losing heat to the cold object, should be equal to the heat that the water gains. And we're assuming this to be equal, minimizing, loss of energy to the atmosphere. And I want you to think about the implications for this. Think back to our previous video. What else does Q equal? Mass times specific capacity times the change in temperature. So if we plug both of those things in to this new equation, we see that So we can take the mass of the metal times the specific heat capacity of the metal times the change in temperature of the metal and do the same thing for water. And usually, not always, but usually we will use this to figure out the specific capacity of a metal. So a lot of lab experiments will give you an unknown metal, and then you heat that metal up super hot, you put it in your calorimeter, do all your temperature measurements, and then you'll be able to calculate the specific capacity of the metal and then look up the value on a table to identify what it is. So in the next video, we're going to do an example of this and kind of relate it to what you'll be doing in your lab experiment.